everybody, this is Miss Bufford, and in this video we're going to talk about periodic trends. So your learning goals here are to be able to illustrate and explain the changes in atomic radius, electronegativity, and ionization energy using the periodic table, and to be able to predict trends of elements based on their placement on the periodic table. So before we talk about the trends themselves, we just want to make sure that we understand a few concepts. Coulomb's law is something that we've discussed in class before, but we've never actually called it Coulomb's law. But the formal name for this idea or this law is Coulomb's law. And it describes the fact that opposite charges are going to be attracted to one another and like charges are going to repel each other. It also states that the closer to these two charges are, the stronger the force between them is going to be. So if they're two like charges and we're trying to get them close together, we're going to experience an increase in the amount of force repelling those two things from each other. But if we have two oppositely charged items and we're pushing them together, the force of attraction is going to get stronger the closer they get to each other. All right. And that's a really important idea when we're talking about the charges in the electrons and the charges in the protons when we discuss the trends that we're going to talk about in this video. The next thing that we need to know is the octet rule. And this is something that you have probably heard a little bit about in middle school science class. But basically, it's saying that atoms of main group elements tend to combine in ways that help them achieve a noble gas electron configuration, or in other words, they want to have a full outer shell of 8 valence electrons. So they all want to have 8 valence electrons because that's a stable configuration for them. So that's another idea that we need to just keep in mind. Oxidation number. This oxidation number refers to the number of electrons that are either gained or lost by an element or an atom in a chemical reaction. And so some elements will tend to lose electrons and some will tend to gain electrons in certain interactions. And the oxidation number just describes, how many electrons that particular atom gained or lost. All right, and it can be positive or it can be negative or it can be zero. One example of this would be if we were to think about lithium. Lithium is a group 1 metal, and it's got 3 valence electrons. It has 3 total electrons, but 1 valence electrons. In group 1, 1 valence electron. And it's a metal, and metals tend to lose their valence electrons in chemical reactions. And so if it loses that 1 negative charge in its valence shell, then it becomes a positively charged. It has a +1 charge because it still has 3 protons, but now it only has 2 electrons. And the net charge there is what the oxidation number describes. And then on the other side of the periodic table, let's say we've got fluorine. Fluorine has 9 protons, and so a neutral atom of fluorine would have 9 electrons, but it would really just have 7 valence electrons. All right, and it wants to have 8, so it tends to pull in a valence electron, and when it pulls in that negative charge, it has a net charge now of -1. All right, and then nuclear charge is a term that I'm going to use to just describe the amount of positive charge in the nucleus, and so basically it's how many protons there are, but I'm just going to use the term nuclear charge because I'm really talking about the positive charge from those protons. We will also talk about the charge in the electron cloud. The electron cloud is just all of the electrons that surround an atom. All right, so let's go ahead and we'll talk about atomic radius first. The atomic radius is the measure from the center of an atom to the outer limit of its electron cloud. So let's take a look at this lithium atom right here. I'm just going to put a little nucleus in here. So there's my nucleus. And if I'm measuring from the center of that nucleus all the way out to the outer edge of that electron cloud, the distance right there is my atomic radius. So that tells me what the radius of that atom is, or what the size of it is. So now let's talk about the trend of atomic radius. So this first bullet point right here, atomic radius is going to increase as I move down a group on the periodic table. So if I'm starting at the top of a group and I'm working my way down that group, then you'll see that, let's say I'm starting up here at hydrogen, I move down this group and the elements or the atoms get larger, all right? And why do they get larger? Well, they're getting larger because each atom down that group has an additional energy level, all right? So it's because they are gaining energy levels as we move down a group. Now, if we look at the trend moving across the periodic table, and this is somewhat true for the D elements, there are some anomalies within the D elements, so we're not going to focus too much on those. We're going to focus mainly on the main group elements, because in this class, that's what we're more concerned with. But if we look at the trend across a period on the periodic table, we notice that the atoms tend to get smaller. All right, and let's think about what we know about these all these elements that are within the same period. So the elements in the period that I just underlined all have 4 energy levels because they're in period 4, right? So they all have the same number of energy levels. What's different about them, though, is that each element down this period has 1 more proton than the last. And so the nuclear charge is growing as we move across this period right here. And although if we're talking about neutral atoms here, the number of electrons is also growing, right? 1 more proton requires 1 more electron to be neutral. And those electrons, though, if we're talking about main group elements, they're all being added to the same energy level. They're all being added to energy level 4. And so as the protons are added and the electrons are added, the charge magnitude of the nucleus and the magnitude of negative charge in that 4th energy level is growing. And as those charge magnitudes get larger and larger, they become more and more attracted to each other. And so the protons in the nucleus kind of squeeze down on those electrons in that 4th energy level. They're squeezing them all closer and closer and closer as those charge magnitudes increase. All right. So that is atomic radius, and that is why we see the trends across the periodic table that we see for that. So now let's talk really quick about ionic radius. And ionic radius just refers to the size of an atom's ion, and it's measured the same way we measure the atomic radius. And so remember, an ion is created when an atom either gains or loses electrons. All right, and so metals tend to lose electrons, and non-metals tend to gain electrons. And so that's something you really want to keep in mind. So when we have a neutral atom and it loses an electron, it becomes positively charged and it shrinks to a smaller size. So if we take a look at these, we've got all of these atoms right here. Boron's a metalloid, but we're going to group it here with this. So when these atoms right here, these are metals, their original size is represented by these gray shells on the outside. All right, that's just what they are originally before they become an ion. When they lose their valence electrons, they lose an energy level because the valence electrons fill that outer energy level, right? So if they lose their valence electrons, they're losing an entire energy level, and so their ions are actually smaller than their neutral atoms will be. All right, and these metals tend to lose electrons just because energetically it's easier for them to lose these electrons. They don't have as much nuclear charge squeezing in on their electrons, so they're not as big. So if you think about the reach from the nucleus on the valence electrons, it's like barely holding on to those valence electrons. And when we're in class, I like to use the analogy of T-Rex arms. So if I'm a metal, I've got T-Rex arms, and it's really hard for me to reach my valence electrons. But if I'm a non-metal, I've got like these super big Stretch Armstrong / Hulk Hogan arms, and I can really hang on to my electrons. And not only can I hang on to my electrons, I can grab onto more electrons. And so these non-metals over here, they tend to gain electrons, and when they gain electrons, though, you think about what happens when we put 2 things that have like charges next to each other. if I have a cloud of negative charges and I add another negative charge in there, they're all going to kind of back up and give each other some more space. All right. The electrons are kind of social distancing here. So we add another electron into the crowd and everybody has to back up a little bit to make some more room for the new addition. So when an ion, a non-metal, becomes an ion, it's gaining electrons. And so non-metal ions that have negative charges are larger than their normal atoms. So if you take a look, remember the gray represents the neutral atom, and the blue in this case represents the negatively charged ion that has an extra electrons, right? So we've put in some electrons. Everybody has to take a step back to make some more room for those electrons to maintain our social distancing. All right. I think I already described all that. All right, let's move on to ionization energy. So ionization energy is the amount of energy that's required to remove an electron from an atom. All right, so how much energy does it take to ionize something is basically what we're talking about. So what characteristics do you think would make it easier to remove an electron from an atom? Well, if we talked about size and nuclear charge already and how they influence how strongly an atom can hold on to its electrons. And so nuclear charge is one factor, and the greater amount of pull from the nucleus, the more difficult it's going to be to remove an electron. It's going to take more energy to pull an electron off that's being held more tightly by the nucleus. All right. And then size, is affected by nuclear charge. So in effect, this is also affecting the size. So smaller atoms hold on to their electrons more tightly, and it's harder to remove those electrons from smaller atoms, all right, because they have larger nuclear charge. And then sometimes electron configurations can also affect the amount of energy. Some configurations provide an unusual amount of stability. And so when we talked about the exceptions to, when we talked about electron configurations and we talked about the exceptions, those exceptions actually make those electron configurations a bit more stable. And so it's harder to remove an electron, just a bit harder to remove those electrons when they're half full. We've got half full d orbitals. So we're not going to talk a whole lot about that, but it is a factor. And then we just always want to remember that metals are the ones that lose their electrons. And when they do this, they get smaller because they lose that energy level. And so you think about what happens if we're getting smaller because we've lost some electrons, then the remaining electrons are held on more tightly, and it's going to take more energy to remove the next electron. And so that's where we get into talking about the different ionization energies. So we've got the first ionization energy, which is the amount of energy that's required to move the first electron from an atom. Then we've got the second ionization energy, which is the amount of energy that's required to remove the second electron from an atom. And this pattern would continue as electrons are, continuously removed from an atom. So if we take a look at some examples here, we've got the first ionization energies represented by a little circle or a dot, and then the second ionization energy is represented by a little diamond for these different elements here. So we take a look at lithium. You'll notice that it doesn't take very much energy to remove lithium's one valence electron, but if we tried to remove an electron from lithium's first energy level, after we removed that valence electron, it would require a tremendous amount of energy, a lot more energy than it took to remove the first one. Beryllium, you can see that it takes a certain amount of energy to remove beryllium's first electron from the valence shell, but beryllium, remember, has two valence electrons, and so they're both in that valence shell. And so it does take more energy to remove the second electron from beryllium, but not quite as much because it's in that same valence shell as that first electron was. And then we see the same pattern with sodium and magnesium. So sodium's got one valence electron, and it takes a lot more energy to remove, a second electron from sodium because that's now not in the original valence shell, right? But magnesium has two valence electrons, so the first one takes a little bit, the second one takes a little bit more. And then we see that same pattern with potassium and calcium as well. All right. Okay, so now we're going to talk about the trend in electronegativity. Electronegativity is the magnitude of an atom's ability to attract electrons towards itself. So what characteristics do we think contribute to this, to an atom having high electronegativity? Well, it's influenced by, the factors that we've been talking about. It's influenced by the nuclear charge and the size of that atom, or how far away those valence electrons are from the nucleus. So if we take a look here, we're going to use period 4 again for our example. Here's period 4. And there's my red pen, it's easier to see. All right, so there's period 4. I'm going to go ahead and just kind of draw a rough potassium atom, and I'm only drawing the energy shell that contains the electrons. So that's energy level 4 right here. All right, here's potassium. And I'm going to go all the way down, and we know what the trend in size is. We've already talked about the size, the trend in atomic size. So bromine is going to be smaller than potassium. All right, so these are on two opposite ends of the periodic table. Electronegativity is very similar to ionization energy. Ionization energy talks about how much energy it takes to remove an electron. Electronegativity is talking about how easy it is for an atom to gain an electron. And so we already talked about the fact, too, that metals are the ones that tend to lose their valence electrons. So we can think of metals as having these little tiny T-Rex arms, all right? So potassium just has barely enough reach to hang on to its one valence electron in energy level 4, right? And its nuclear charge isn't really strong enough to pull in any more electrons. All right, so we've got this tiny nuclear charge here, one valence electron that it can barely hold on to. So think of potassium in the group 1 and group 2 atoms as having these little bitty T-Rex arms. And as we move down the period, our arms get longer and longer and longer until eventually when we get down here to bromine, we've got these like super stretch Armstrong Hulk Hogan arms with these huge muscles, and they're really good at holding on to their electrons. And not only are they good at holding on to their electrons, their influence kind of extends beyond that valence shell, and it makes them really good at attracting more electrons towards themselves. So if you think about the positive charge from bromine radiating a little bit beyond its electron cloud, it's got these little positives out here kind of attracting electrons towards itself. All right, bromine's got 7 valence electrons, 2, 3, 4, 5, 6, 7. It only needs 1 to have a full outer shell, and it pulls in that electron very easily. All right, so you can think of the group 1 elements as having T-Rex arms, and this is like stretch Armstrong. This is better in person too because I can do all the movements. But anyways, hopefully that visualization of T-Rex and stretch Armstrong on the other side of the periodic table are helpful in you being able to see, the difference in how easily these are able to hold on to their valence electrons, but not necessarily that, because electronegativity is about their ability to attract more electrons towards themselves. T-Rex can't really reach far enough to pull in any more electrons, but Stretch Armstrong can definitely reach out beyond its electron cloud and pull in more electrons. All right. Electronegativity is really important when we talk about chemical bonding in the next unit, because it's the difference in electronegativity between the atoms involved in the chemical reaction is really what determines what type of bond it's going to be formed. And so we'll talk a lot more about that in our next unit after Thanksgiving break. So hopefully this video was helpful. Actually, one more thing that I would like to do is I'm going to come back here to this picture, and I'm going to add some information to this. So this shows you the trend in ionization energy, but the trend in electronegativity is that it's going to increase. So electronegativity increases going across the period on the periodic table, and it also increases, it follows the same trend as ionization energy. So that's electronegativity here and here. All right, and then atomic radius is going to increase going the other way. So if we're talking about atomic radius, which I'll make that a different color here, I'll make that green. Atomic radius is going to increase going the opposite way. So increases going this way, and it increases going down. So these would be good diagrams to put in your notes. It's always a really good idea to have, a visualization of the trends so that you can have a quick reference to look at when you're asked questions about whether a certain atom is more electronegative or larger or has a higher ionization energy than another one. All right, so again, I hope this video was really helpful for you guys. Let me know if you have any questions. I'm happy to help. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.